Good afternoon, everyone. Today I'll be presenting our work titled Empowering Machine Learning Assisted Kernel Decisions with eBPF-ML, conducted at Columbia University in collaboration with Georgios and Professor Kostis Kaffes. Our goal is simple: to bring efficient, safe, and real-time ML-powered decision making into the operating system kernel. In this short talk, I'll first introduce our motivation and ground the problem, why ML inside the kernel is appealing, yet so hard to deploy. We look at when it's actually worth learning over a heuristic, then consider the hardware landscape: CPUs, discrete accelerators, and on-core matrix engines. Having established the context, I'll walk through our design vision for eBPF-ML, which includes minimal algebraic primitives, verifier-friendly bounds, and adaptive backends that pick the best available hardware path. We'll close with what this enables and the questions we are opening up to the community. Machine learning has already transformed user space systems. The next frontier is the operating system kernel, where decisions about scheduling, I/O, memory, and power states happen on a microsecond scale. Optimizing these kernel paths can directly reduce latency and improve efficiency. Yet, in practice, ML in kernel deployments remain rare. Why? Because existing approaches either embed bespoke ML logic deep inside the kernel, which requires years of engineering and makes the kernel fragile, or offload inference to the user space, which introduces tens of microseconds of syscall and DMA overhead while competing with user workloads. Neither of these approaches is sustainable and robust enough for production systems. This leads us to our key requirements. We need minimal code churn. Kernel rewrites are just not realistic. We need strict latency guarantees. Every microsecond matters. And we need architectural portability. Solutions must survive across hardware generations. This is where eBPF comes in. eBPF is already widely used as a safe, dynamic, and hot swappable mechanism for extending the Linux kernel. Our insight is that it can also be the substrate for ML inside the kernel. Of course, not every problem calls for ML. For ML inside the kernel to make sense, two conditions must hold. Accuracy must significantly exceed heuristics to produce user-visible gains, and inference latency must be small enough that these gains are not erased. Past systems show mixed results. Yawn, for example, improved tail latency only under low request rates. Lake degraded NVMe throughput by 47% on light workloads because GPU batching overhead outweighed the benefits. The lesson is clear. There is no one-size-fits-all model. The framework must let operators choose the simplest model that balances accuracy and latency for their deployment, and that choice must be swappable without having to rebuild the kernel. Now let's look at hardware. Discrete GPUs provide high throughput but suffer from DMA latency and require vendor driver hooks, unsuitable for kernel paths. Scalar CPUs are safe but too slow for even modest neural networks. CPU-based accelerators, like Intel's advanced matrix extensions, offer a sweet spot: near GPU performance, at least for moderately complex models, without costly data transfers. Here we define model complexity not by layers or parameters, but by inference latency. If a model can't meet the latency budgets on a scalar CPU, it requires acceleration. Our experiments with workloads like Linux show that GPUs only outperform AMX at large batch sizes, a scenario rare in production. For most real deployments, AMX achieves 1.5 to 2.5x lower inference time than CPU and outperforms GPUs at practical batch sizes. Let me now walk through our design vision. We propose eBPF-ML, an architectural extension that enables safe, hot swappable ML inside the kernel. The design has three pillars: generic primitives, adaptive backend, and preservation of safety. Generic primitives provide minimal linear algebra helpers, such as matrix multiply, bias add, and activations. We avoid hard-coding models or accelerators to keep it portable. Then at load time, the kernel picks the best available backend, AMX, AVS, or other SIMD instruction sets, or just the scalar CPU. This ensures incremental adoption as hardware evolves, while preserving eBPF's core portability. Today, the eBPF verifier approximates worst-case cycles statically. That works for scalar integer code, but a matrix helper's latency depends on both the data shape and the backend. One question we are opening up is whether we can extend the verifier's metadata model so that helpers can annotate an upper bound function of the input dimensions. That would allow cycle bounds to be enforced even when hardware acceleration is involved. A second key issue is managing matrix accelerator state, particularly with Intel AMX. AMX exposes tiles which are part of the processor's extended context. That context is managed through the Xsave XRStore mechanism, but it is not enabled by default in Linux. This sketch leaves room for exploration. How expensive should our algebra helpers be? Where do we draw the line between verify static checks and runtime accounting? And what should the compiler pipeline look like to emit BPF-friendly kernels? We don't claim to have solved these questions. We are seeding the discussion and setting up the design envelope. This diagram shows how the decision flow works in practice. A standard kernel routine reaches a point where it needs to make a policy decision. Based on a user configuration, it can either follow a traditional heuristic-based path or invoke our ML-based eBPF routine. Inside the eBPF program, our framework makes an adaptive choice. If the model is complex enough to require acceleration, it invokes the accelerator backend. Otherwise, it falls back to the standard CPU, ensuring the best performance for the given task. The results are then fed back into the kernel routine, and the execution continues. To conclude, our key insight is that eBPF can be extended to safely host ML inside the kernel, bridging the gap between heuristics and heavyweight offload mechanisms. We provide a design sketch with generic primitives, adaptive hardware support, and verifier safety. The broader vision is kernels capable of intelligent, real-time decision-making, with ML integrated seamlessly into critical paths. We hope this work seeds further exploration of verifier extensions, hardware adaptation strategies, and compiler pipelines for ML in eBPF. Thank you, and we look forward to your questions.